Hello, good morning to one and all. My name is Shifa Mohammad Ayaz, and I'm a third year electronics student. And today I'm going to teach you my seventh experiment, that is design of a Schmitt trigger and its application. So let's get started. So the aim of our experiment is to implement an inverting Schmitt trigger using op-amp, then to develop an astable multivibrator based on the Schmitt trigger principle. The third one is to modify the astable multivibrator circuit to form a triangular wave generator. And finally, to modify the astable multivibrator circuit to form a sawtooth wave generator. The simulation tool here we are going to use is LT Spice. So basically, what is the Schmitt trigger? So for an inverting Schmitt trigger, we are going to feed the input waveform at the inverting terminal, and some part of the non-inverting terminal is fed back to the output terminal of the op-amp. That is, we are providing a positive feedback to the op-amp. So from the non-inverting terminal, we are going to feed some fraction part of it to the output terminal. Now when the V in, this is your V in, is slightly greater than the Vref, then the output becomes minus Vsat, and if the V in is slightly less than the negative Vref, then the output becomes positive Vsat. So hence the output is either plus Vsat or minus Vsat depending upon these two states. With depending upon these states, these states can be controlled by the resistors R1 and R2. So this is how the inverting Schmitt trigger is actually looks like, and this is the transfer characteristics of the inverting Schmitt trigger, or also known as the hysteresis curve. Okay, and so let's get started. Okay, so this is the basic calculations required for the inverting Schmitt trigger. Your R1 is 1.5k and R2 is considered to be 1k. So the threshold voltage is calculated to be as 6 volt. So we are going to keep our upper threshold voltage as positive 6 volts, and the lower threshold point to be as minus 6 volts. So depending upon these two threshold level, my output will switch from positive or negative Vsat. So let's see the waveform. So this is how my inverting Schmitt trigger looks like. Okay, so this is how the inverting Schmitt trigger looks like. As I said, Vin is fed to the inverting terminal, and some part of the non-inverting terminal, or some part of it is fed as a positive feedback to the V out terminal. And these are the two voltage divider. These two R resistors form the voltage divider network, and these values have been used according to the calculations done, and VCC and VEE is being provided from the voltage sources. So here I'm considered for an input sine wave for 8 volts, and 10 kilohertz is my frequency, and this is the stop time for it. So let's run the circuit and check the output. So let's plot the V in and V out. So yeah, so at greater frequencies we will see clipping at the output waveform, which is being observed over here. So for 10k I'm getting this sort of an output. This is due to because my op-amp is driven into saturation, so clipping is being observed at the output. So similarly, I've taken these values for different levels of frequency. So for 50 hertz, for a sinusoidal wave, I get a very good, much perfect square wave as an output. Then for 500 hertz also I'm getting a better output, satisfactory output. But as my input frequency keeps on increasing, the op amp is then driven into saturation and the clipping of the waveform is being seen. So for 10K, this is what I had shown you. Moving on to the next part, we have an stable multi-vibrator. So the stable multi-vibrator is basically an application of Schmitt trigger only, but it here is an astable multi-vibrator also acts like an oscillatory circuit where it generates a rectangular output waveform using this RC network over here connected to the inverting terminal. And the voltage divider network is connected to the positive terminal, that is the non-inverting terminal. So depending upon the charging and discharging, we get to see these sort of waveforms, triangular sort of waveforms. So here are some of its calculations being shown over here. The calculations are such that this is the formula for the RC time constant for the astable multi-vibrator. So the time duration is being calculated by using this formula, and this is derived from the charging and discharging of the waveforms. So that time is being calculated and clubbed together, which shows us the time duration. Beta is the feedback factor, that is the voltage divider network associated with it. So for a given frequency, that is 1 kilohertz, I've designed this circuit. So according to it, according to the calculations, I've got my RNC values. So using them, I have made the circuit. So let's simulate this one now. So this is how my astable multi-vibrator looks like. Okay, here is my, again this is the positive feedback which is being fed again to the output terminal. A capacitor is connected to the inverting terminal, and as I told you, according to the calculations, I've taken my R and C values. So now let's simulate this circuit and check the output. So this is the capacitor charging and discharging, and the V out. So the V out is basically a square waveform. So from triangular waveforms, I'm getting some sort of rectangular square waveform at my output. So this output is actually this output is dependent upon the uh, RNC network, and basically it's upon the charging and discharging time of the capacitor you get to see such sort of waveforms. So that's it about the stable multi-vibrator. Moving on to the next, we have a ramp generator. Yes. Yeah, so the ramp generator is also known as a triangular wave generator. Again, it is an application of the astable multi-vibrator. So the first stage, if you see, same as the astable multi-vibrator. The only change we have added over here is the Zener diode and an integrator circuit over here. So that's how you check the output. So this is so a ramp generator is an application of the stable multi-vibrator. So let's simulate the circuit and check the output. Again, the R and C values are chosen according to the formulas as I had shown you all previously. So for over here, we are gonna check the stage before this. So here I'm getting a square waveform as I've shown you, and here I'm getting a triangular waveform if you see. So the square wave output is being provided from my stable multi-vibrator, and due to the addition of this new second stage, I'm getting this sort of a triangular waveform at my output. So now showing you further, we move on to the sawtooth generator circuit. So this is how your sawtooth generator circuits look like. Again, similar configuration is built upon over here, and here I'm giving a positive VCC to the uh, biasing resistors over here. That's how my circuit looks like. And now let's check the output. So similarly as I'd shown you for the previous stage, so again we are getting some sort of pulses, that is square waveform actually. This is my input to this circuit, and this is the output. So this is how the sawtooth waveforms look like. So that's how the output is. Only changes that we are making the changes in the charging and discharging time of the capacitor, due to which the waveforms will undergo a change. So that's it regarding to my explanation with this experiment. Thank you.